2, 1, go. Hey everybody, I'm Rob Yates. This is Braden Mara. This is Matthew Kogut. We're two guys tank tops, one guy t-shirt. We're here today to talk about fluids and the world around us. But primarily, we're going to talk about why does a curveball curve. But first, let's see a demonstration. Whoa, that was pretty amazing, wasn't it? Well, why do you think that ball curved? What do you think made it do that? Was it some ghost, Casper, trying to play tricks on us? Let's see if Matthew Kogan can explain a little bit.
So in order to explain the curveball, we rely on Bernoulli's Principle, which states that within a horizontal flow of fluid, points of higher fluid speed have lower pressure, or have less pressure than points of slow fluid speed. And this can better be explained with the Bernoulli equation given here. In order to use this, we have 4 assumptions that we must have. So first, the fluid is at steady state, which means that its properties don't change with respect to time. The fluid is incompressible, so its density is constant. The fluid is frictionless, and it flows along a streamline. So using this equation, we can see that given a point, as the velocity increases, the pressure is going to have to decrease, since both sides of the equation are constant. And then in the next part, Braden will explain how this applies to the curveball as it's flying through the air.
So you're probably wondering, Braden, that was a bunch of gibberish. How in the heck does that apply to a curveball? Well, let's look at this diagram and I'll explain real quick. If we look at this, you see the streamlines below the ball is a lot tighter than the one at the top of the ball. This is because due to the rotation of the ball, the velocity of the air underneath the ball increases. Results of that, since the velocity increases, the pressure below the ball decreases. And with the difference in pressures, the higher pressure causes the ball to go down. And that's pretty much it for the demonstration.
So now we know about the curveball. Let's look at another example. Let's look at an airplane wing. So this is our airplane wing. We have a little slope right here, a little shape of it. Now, let's look at the fluid particles as that airplane wing is going to move through the fluid. So you're going to have these, this flow, these streamlines going underneath the airplane wing. And you see how they're going to be pretty big, as our example earlier with the curveball. Then you have this fluid moving over top of it, this air moving over top. And it has to go over this slope and then go back down. So this creates a lot higher velocity because it has to go over this slope. So it has to go a lot faster to go through or to get past this wing. So this lower velocity, or this higher velocity at the top and lower pressure, is going to cause this pressure at the bottom to push up. And that's going to create lift. And that's what we see in an airplane. And that's all because of the Bernoulli Principle.
So now we all know a bit more about the Bernoulli Principle. To sum up from the equation, we saw in the example of the curveball how the increased air velocity at the bottom of the ball caused the pressure to push the ball down. So now next time you're in the world, you can apply this equation to explain another natural phenomenon that you may find.